Hello and welcome to the AI Research Roundup. I'm Alex, and today is May 9th, 2025. We're discussing an ICLR conference paper, SD-LoRA, Scalable Decoupled Low-Rank Adaptation for Class Incremental Learning, published just over 3 months ago. This paper explores how AI models can learn new information sequentially, especially in class incremental learning. That's when new categories are added over time, without catastrophic forgetting, where they forget older knowledge. The authors introduce Scalable Decoupled Low-Rank Adaptation, or SD-LoRA. This Scalable Decoupled Low-Rank Adaptation method cleverly separates how it learns the size and direction of changes made through low-rank adaptation, or LoRA, which are efficient adjustments to large foundation models. This Scalable Decoupled Low-Rank Adaptation approach aims to overcome limitations in existing methods. Now, this table compares various continual learning methods. That's the general field of AI learning sequentially, based on 3 desirable properties. These are being rehearsal-free, so no need to store old data; inference efficiency, meaning it's quick when making predictions; and end-to-end optimization, where all parts are tuned together. The table clearly shows that Scalable Decoupled Low-Rank Adaptation is the only method listed that successfully achieves all 3, which is a significant advantage. Alright, so building on those desirable properties, this figure really helps visualize how Scalable Decoupled Low-Rank Adaptation works differently. On the left, Part A shows standard low-rank adaptation. It adjusts the model's pre-trained weights, its initial settings, using a parameter update, which is a change to these settings, derived from 2 trainable matrices. Now, Part B illustrates the Scalable Decoupled Low-Rank Adaptation. For each task, it uses decoupled low-rank matrices for direction, frozen for old tasks, and a learnable low-rank adaptation magnitude, this alpha value, to scale their impact. New tasks get new directions and magnitudes. This decoupling is key. Okay, so this next figure delves deeper into the learning process of Scalable Decoupled Low-Rank Adaptation. Part A shows the least squares fitting residual, essentially a measure of difference between a newly learned direction and previous ones. It increases over iterations, indicating new tasks bring distinct directional needs. Then, Parts B and C plot the learned low-rank adaptation magnitudes for tasks on the ImageNet-R dataset. These plots show that directions learned from earlier tasks are treated as more critical, generally maintaining higher magnitudes. In contrast, magnitudes for later tasks tend to be smaller, suggesting these later directions act as minor refinements to the model. Building on that idea of how directions are treated, this next figure provides more evidence. Part A is a heat map showing distances between optimal weights. Those are the best model settings for each task relative to the original foundation model weights. The darker blues indicate these task-specific optimal weights are actually closer to each other than to the initial foundation model settings. Then, Parts B and C compare average accuracy, basically how often the model is right, for vanilla LoRA, which is standard low-rank adaptation, against LoRA with a fixed initial direction. Fixing that first direction clearly helps maintain higher accuracy as more tasks are learned. So, this next figure really brings home how Scalable Decoupled Low-Rank Adaptation avoids forgetting. Part A illustrates the learning trajectory. That's the path the model's internal settings take as it learns. You see, Scalable Decoupled Low-Rank Adaptation guides the model towards an overlapping low-loss region, an area of settings where the model makes few errors on both old and new tasks. Parts B and C then plot classification accuracy. For standard low-rank adaptation, accuracy on the first task drops significantly when learning the second, a classic case of catastrophic forgetting. But with Scalable Decoupled Low-Rank Adaptation, accuracy for both tasks remains high, showing it finds that shared sweet spot. Okay, so to see how this all plays out in numbers, this table presents key performance results. It compares different methods on the ImageNet-R dataset, a benchmark for image recognition, across an increasing number of tasks, from 5 up to 20. We're looking at average accuracy, or ACC, which is just how often the model gets it right on average, and average anytime accuracy, or AAA, which also considers performance throughout learning. Across all task counts, Scalable Decoupled Low-Rank Adaptation and its variants consistently achieve the highest scores, especially as more tasks are added, really underscoring its effectiveness and scalability. Alright, beyond just accuracy, this table focuses on efficiency for 20 tasks on ImageNetR. It compares methods using GFLOPs. That's Giga Floating Point Operations per Second, measuring computation, learnable parameters, the model's adjustable settings, and stored features or data kept from old tasks. Scalable Decoupled Low-Rank Adaptation and its variant Scalable Decoupled Low-Rank Adaptation with Rank Reduction, or SD-LoRA RR, are impressive. Both achieve GFLOPs of just 35.12, about half of many other methods. Scalable Decoupled Low-Rank Adaptation with Rank Reduction is particularly lean with only 0.23 million parameters, and crucially, neither method requires stored features, highlighting their excellent scalability. So to wrap things up, it's clear that Scalable Decoupled Low-Rank Adaptation offers a really smart way for AI to learn continuously. We've seen how by separating the strength or magnitude and the specific direction of its internal updates for each task, it tackles catastrophic forgetting. Remember, that's the common issue where an AI forgets previously learned tasks when new ones are introduced. And this all applies to those large foundation models, the powerful pre-trained AIs, helping them learn efficiently without needing to store old data. It's a great balance. Thanks for tuning in to the AI Research Roundup.